So, let me ask you something. What if I told you that our entire digital world, I mean everything, your smartphone, the cloud, all the advanced tech we rely on, what if it all depends on a single company? A company you've almost certainly never heard of. Well, that's exactly what we're talking about today. We're going to pull back the curtain on this unseen giant and figure out how it ended up holding the keys to, well, our future.
And this quote, wow, it just nails it, doesn't it? It gets right to the heart of the matter. You know, we think of the global tech industry as this massive, unstoppable force. But the reality? It's all balanced on a knife's edge. It's way, way more fragile than you'd ever imagine.
And yeah, that question I just asked, it's not some hypothetical thought experiment. It's real. Today, we're going to reveal the one company that sits at the absolute center of it all. The one that quite literally makes everything else possible.
Okay, so before we get to the company itself, let's just zoom out for a second. We need to appreciate the sheer scale of the world it controls. Because this isn't just about faster computers or fancier phones. We're talking about the very foundation of modern life.
I'm talking about the global semiconductor industry. And look at that number. Over $500 billion. It's a colossal industry. You can think of it like the nervous system for the entire global economy. It's that important.
Right? And at the heart of that whole industry, it's the integrated circuit. You know it as the microchip. These are the tiny little brains powering literally everything, from your car to your coffee maker. And here's the crazy part. These incredibly complex circuits are basically printed onto silicon. They use super focused light to do it in a process called photolithography. Now, remember that word, photolithography, because it's the key to this entire story.
So that massive $500 billion industry and that critical printing process, photolithography, it all leads us to one single company, in a quiet little town in the Netherlands, of all places. The company is ASML, and they are that singular choke point.
Okay, so the big question is how? How on earth did one company from the Netherlands end up in this unbelievably critical, monopolistic position? Well, you're not going to believe where their journey started.
Believe it or not, for its first decade, ASML was basically in a constant fight for survival. Seriously. They had this culture of what they called firefighter engineering, which meant they were literally racing out to customer sites to put out fires and fix problems on the spot, because they just didn't have the money or resources to get everything perfect back in the lab.
So forget everything you picture when you think of a tech company. You know, those gleaming Silicon Valley campuses. The story goes that their first office was nicknamed the Leaky Shed, and it's not a joke. They actually needed buckets to catch the rainwater dripping from the ceiling. It's just a universe away from the super advanced, ultra-clean environments they're known for today.
I mean, they were the absolute definition of an underdog. Imagine this. You're stepping into a heavyweight boxing ring, and in the other corner are the reigning champions, Japanese giants like Nikon and Canon. These companies had almost unlimited cash and incredible manufacturing power. ASML, they had, well, neither of those things. Not even close. So, since they couldn't possibly outmuscle their competition, they knew they had to outthink them. And they came up with an idea that would completely flip the script on the economics of making chips.
Their big breakthrough was a machine called the PASS 5500. See, before this, lithography machines were these giant one-piece things. If you wanted to upgrade, you had to throw out the entire multi-million-dollar system and buy a new one. It was insane. But ASML came along and designed their machine like a high-tech Lego set. So instead of scrapping the whole thing, customers could just swap out a piece here, a part there, to get the newest technology.
This was an absolute game changer. It saved customers a ton of money, but, and this is really important, it helped ASML build a super strong relationship with the company that was, at the time, just a young chip foundry called TSMC. And that partnership, it would turn out to be the most important one in the industry. As TSMC grew into a titan, they pulled ASML right up along with them.
Okay, so fast forward to the early 2000s. ASML is no longer the underdog, they're a serious contender. But their next big idea? Well, it wasn't just another improvement. It was the knockout punch that would make them the undisputed champion of the world.
Here was the problem with everyone else's machines: a huge inefficiency. The lens, which is by far the most complicated and expensive part of the whole system, was just sitting there doing nothing for half the time. It was just waiting around while another part of the machine was busy measuring the silicon wafer.
So ASML's solution was just genius. They called it the Twin Scan Platform. And the idea was simple: do two things at once. They built it with two stages, so while one silicon wafer was being exposed to the light, getting printed, a second wafer was being measured and mapped on the other stage at the exact same time. Then poof, they just swapped places. The lens never had to wait. It was constantly working.
This idea of parallel processing was brilliant. It meant that super expensive lens was working pretty much nonstop. And what did that lead to? A massive, massive jump in productivity. We're talking about how many wafers they could process per hour. They were just blowing their competitors out of the water.
And that single advantage, that huge leap in productivity, that was all it took. By 2002, ASML had left its Japanese rivals in the dust. They were now the undisputed market leader. They had officially won the lithography wars.
So, that's the history. It's an amazing journey, right? From a leaky shed to world domination. Now let's bring it all back to today. Let's really understand why this one company has become the singular choke point for, well, all of our technological future. It all comes down to three letters: EUV, Extreme Ultraviolet Lithography. This is the only, and I mean only, technology on the planet that can print the microscopic circuits we need for the most powerful, cutting-edge chips. And ASML? They are the only company on Earth that can build an EUV machine, period. No one else can do it.
So let's just be crystal clear about what's at stake here. Without ASML and their machines, technological progress, it just stops, dead in its tracks. You can forget about more advanced AI, you can forget about next-generation military hardware, the famous Moore's Law, that engine that has driven 50 years of progress, it would just grind to a halt.
Okay, so let's set the scene. We're talking the early 2000s, and the entire semiconductor industry, the engine of our whole modern economy, was about to slam headfirst into a wall. A physics wall. And I mean, a real fundamental law of physics was about to stop Moore's Law completely dead in its tracks. See, for decades, the playbook for making chips faster and smaller was actually pretty simple. Just keep using light with shorter and shorter wavelengths to etch smaller and smaller circuits onto silicon. They went from visible light to UV, then down to what's called deep ultraviolet, or DUV, using a laser with a 193 nanometer wavelength. But right there, that's where everything just stopped. Now, the next logical step, right? It seemed obvious: a 157 nanometer laser. Big players like Nikon and Canon, they poured billions into making it happen. But it was a total bust, a dead end. The special lenses they needed were just awful, they were brittle, insanely expensive, and the optics were just flawed. The entire industry was stuck, period. So while everyone else was trying to just smash their way through this physics wall, this Dutch company, ASML, they made this incredibly smart, kind of counterintuitive bet. They figured, hey, why try to break the wall when we can just bend physics around it? And their big idea, it was called Immersion lithography. It's genius, really. They figured out that if you replace the tiny gap of air between the lens and the silicon chip with a single drop of ultra-pure water, you could basically trick the light. You see, water has a higher refractive index than air, which means it bends light more sharply. This let them focus the light way, way tighter. And the best part? They could print much smaller circuits using the exact same 193 nanometer laser that everyone else was stuck with. It was a total game changer. And oh boy, did that bet pay off. It was spectacular. While their competitors were sitting on billions of dollars of useless tech, ASML's market share for these high-end machines just exploded, from around 30% to over 80%. Just like that, they had bought the entire industry another decade of progress. But here's the thing. Immersion was just a clever hack. It was just buying time. To really get to the next generation of chips, what the industry needed was a revolution. I mean, a genuine quantum leap. They had to go from deep ultraviolet to something called extreme ultraviolet, EUV. And look, this wasn't just another small step down the ladder. This was like jumping to a completely different planet of physics. We're talking a jump from 193 nanometer wavelength all the way down to just 13.5 nanometers. It's a huge leap. At that tiny wavelength, light starts behaving more like an X-ray. It gets absorbed by pretty much everything, even air. And glass, forget it. So that meant no more lenses, and the whole machine had to operate inside a near-perfect vacuum. Okay, and this is where the story gets a little political. So a lot of the early foundational research for EUV was actually happening in US national labs. But the US government, still kind of spooked by Japan's dominance in the 80s, basically blocked Japanese companies like Nikon and Canon from getting their hands on the tech. Instead, they tapped ASML, a European company but a NATO ally, to take the lead. And that one decision, right there, it basically handed ASML the keys to a future global monopoly. So, right, how in the world do you even make this kind of light? It's not like you can just build a bigger laser pointer. The solution they finally came up with is, well, it's something straight out of a sci-fi movie. They literally decided to create a tiny star inside a vacuum-sealed box. Okay, so get this. Here's how it works. A generator shoots these microscopic little droplets of molten tin into the vacuum chamber. First, a quick, low-power laser pulse, the pre-pulse, zaps the droplet. But it doesn't vaporize it. Nope. It just flattens it into a perfect little pancake to give it more surface area. Then, just microseconds later, a second, absolutely massive CO2 laser, we're talking powerful enough to cut through steel, obliterates that little tin pancake. And the machine does this with pinpoint accuracy, 50,000 times, every single second. Think about that. It's hitting a microscopic target that's zipping along at over 160 miles per hour, and it nails it 50,000 times a second. The timing and precision involved are just, it's almost impossible to wrap your head around. So when that main laser hits, that tin instantly vaporizes into a plasma that's heated to 220,000 degrees Celsius. Let me say that again. That is nearly 40 times hotter than the surface of our sun. And for just a fraction of a second, as that superheated plasma cools, it lets out this flash of light with a perfect, beautiful spike at exactly 13.5 nanometers. They really did it. They created a star on Earth to power your phone. But okay, creating the light, that was only half the battle. Not even. Now they had to figure out how to aim this ridiculously fragile light, and they had to stop this tiny star from basically destroying the entire multi-million-dollar machine from the inside out. So, since glass is a no-go, it just eats UV light, the machine uses a series of incredibly complex mirrors instead of lenses. And when I say complex, I mean these are probably the most perfect, most precise objects humanity has ever created. This quote from one of the engineers really puts it in perspective. If you blew one of these mirrors up to the size of the Earth, the biggest bump on it would be smaller than one of your hairs. It's insane. All right, so new problem. How do you protect the world's most perfect mirror from a 220,000 degree plasma explosion happening 50,000 times a second right next to it? Because that blast, right, it's spraying super fast tin shrapnel everywhere. It would coat those ridiculously expensive mirrors and ruin them in literally minutes. The solution they came up with is just a beautiful piece of chemistry. First, they pump hydrogen gas into the chamber. This acts like a little cushion, slowing down most of the tin debris. But then, and this is the genius part, the EUV light itself zaps that hydrogen gas and turns it into these super reactive things called hydrogen radicals. These radicals are like little Pac-Man. They go around and chemically react with any tin that does manage to splat onto the mirrors, turning it into a totally new gas that they can just vacuum out of the chamber. It's a constantly running, self-cleaning system. It's what allows these machines to run 24/7 for months at a time. So by solving one impossible physics problem after another, from bending light with water to making a star in a box to designing mirrors that literally clean themselves, this one company, ASML, managed to put itself in this completely unique and incredibly powerful position. Let's be clear, ASML is the only company on planet Earth that can build these machines. This isn't just a market lead. It is a 100% total monopoly on the single most important tool in the modern world. Without this one machine, there are no iPhones, no AI, no internet servers. Our modern world just doesn't exist. Now, they don't actually make the chips themselves. What they do is build these unbelievably complex machines that print the chips. And when it comes to the most advanced chips on the planet, they're the only game in town. We're talking a 100% monopoly. But to really get how they pulled this off, we can't start with their success. No, we have to go back to their moment of absolute crisis, a time when the entire company was teetering right on the brink of failure. And that crisis, it had a name, EUV. That stands for Extreme Ultraviolet Lithography. This was supposed to be the holy grail, the tech needed to etch these microscopic circuits for the next generation of chips. The problem was, this holy grail was also a billion-dollar failure that was pushing ASML to the edge of collapse. You see, developing EUV wasn't just some ambitious project. It was a total moonshot, and for over a decade, it was a bet that just refused to pay off. Billions of dollars were getting poured into R&D for a machine that was, for all intents and purposes, a very, very expensive paperweight. This timeline really puts the pressure into perspective. I mean, look at it. They started R&D way back in 2000. 12 years and billions of euros later, they had sold exactly 0 machines. They had earned 0 revenue. The clock was ticking and the money was almost gone. And here, right here, is the technical problem in a nutshell. For these EUV machines to be profitable for their customers, the light source inside needed to hit 250 watts of power. But in 2012, after all that time and all that money, they were stuck at less than 10 watts. They weren't just missing the target, they were on a completely different planet. So facing total financial and technical collapse, ASML did something radical. Instead of going to the banks for more loans or finding traditional investors, they went to the very people who were waiting for their machines and made them an offer they just couldn't refuse. And this quote just says it all. It perfectly captures the genius of their move. ASML went to its biggest customers, we're talking the titans of the chip industry, and they basically said, look, stop waiting for us to solve this problem. Instead, pay us to solve it with you, and you can own a piece of the solution. They literally turned their customers into their partners. And as you can see, the biggest players in the world came to the table. Intel led the way, grabbing a massive 15% stake, and its biggest rivals, TSMC and Samsung, they followed right behind. Just think about that for a second. They were funding their key supplier to build the very technology they would all need to survive. It's kind of wild. And the result? A staggering 4 billion euro cash injection. This wasn't just a lifeline. It was a war chest. It gave them the money and, maybe more importantly, the 5-year runway they needed to finally crack the EUV puzzle. Okay, so here's the crucial point. This wasn't just about the cash. It was a 2-for-1 masterstroke. First, it gave them the money to go out and buy Cymer, the American company that was struggling to build that all-important light source. This brought that critical tech directly under ASML's control. Second, and this is the really brilliant part, it locked the world's biggest chip makers into the ASML ecosystem. With their own money now on the line, there was no way they were going to fund a competitor. Just like that, the market was effectively closed. So how did this one brilliant move build an entire fortress? Well, it's because that co-investment deal wasn't just a one-time fix. It actually became the blueprint for a business model that is, today, virtually untouchable. See, ASML doesn't operate like a normal manufacturer. They call themselves a system integrator. They don't even try to build everything themselves. Instead, they act as the architect, the conductor of this vast, vast network of super specialized partners. And this chart is just mind-boggling. An EUV machine has over 100,000 components. But look at this. ASML only builds about 15% of the value in-house. A whole 85% comes from their supply chain. Their real genius isn't in making everything. It's in being the one indispensable conductor for an orchestra of 800 other suppliers. They call this model open innovation. And instead of keeping secrets, which is what most tech companies do, they share their long-term technology roadmap with hundreds of their key suppliers. This gives partners like Zeiss and Trump the confidence to pour millions into R&D years in advance because they know exactly where ASML is going. It creates this deeply interdependent web where everyone's success is tied together, a web no single company could ever hope to build on its own. But don't get me wrong, ASML is also ruthless about controlling the absolute bottlenecks. When that light source from Cymer wasn't working, they didn't just partner, they bought the whole company. To create the most perfect mirrors ever made by humans, they bought a huge stake in the legendary company Zeiss. And they use IMEC as this kind of neutral playground, where they, their customers, and their suppliers can all get together to perfect the tech of tomorrow. It's a system of total collaborative control. So what's the end result of all of this? Well, it's a complete redefinition of what a monopoly can even look like in the 21st century. The key takeaway really is this. ASML's monopoly isn't just based on having the best tech. It's based on a business architecture that is almost impossible for anyone else to replicate. They built this incredible ecosystem where their customers are also their investors, their suppliers are their long-term R&D partners, and everybody is locked into the very same technological roadmap.
Okay, so you've got to understand, everything here starts at a scale that's just hard to even wrap your head around. We're in a world where one tiny little speck of dust isn't just an annoyance, it is a full-blown catastrophe.
That single particle can wipe out millions of dollars worth of microchips in the blink of an eye. And that is the problem ASML had to solve.
So how do you fight a microscopic enemy? Well, apparently you do it with a machine that weighs 180 tons. That's right, the size of a city bus, heavier than a blue whale. It's this wild contrast, right? A total behemoth, built to conquer an enemy you can't even see.
So where on earth does something like this come from? As you can probably guess, its origin story is just as extreme as the machine itself. It all starts with its birth, forged in what is probably the cleanest place on the entire planet.
It's put together in Veldhoven, in the Netherlands, inside these insane, hyper-controlled clean rooms. And just to put that into perspective for you, the air in these rooms is literally thousands of times cleaner than the air in a hospital operating room. It has to be, because any slip-up, any stray particle could cause what they call a killer defect. And yeah, a killer defect is pretty much exactly what it sounds like. It's one microscopic flaw that can cascade across an entire silicon wafer, making every single chip on that wafer totally worthless. The stakes are just unbelievably high, which is why that whole assembly process is so obsessive.
But here's the thing. Building this machine is really only half the battle. Once you've painstakingly put it together, you run into an even crazier problem. How in the world do you ship a 180-ton, incredibly fragile piece of equipment across the globe? This isn't just shipping, it's a mission to move a mountain.
The whole process is this massive logistical operation that honestly feels like something out of a military deployment. First, you have to carefully take the whole thing apart. Then you pack all those pieces into dozens of special containers, fly them on multiple jumbo jets, and then use a massive convoy of trucks to get them to the factory.
And I just want you to let that number sink in. 40 freight containers. Think about that. That's not for a whole factory's worth of equipment. That's for one machine.
And to get those 40 containers to customers in places like Taiwan or the US, you need up to 4 Boeing 747s, 4 jumbo jets. It's a massive airlift, all for a single system. Absolutely incredible.
And let's just circle back to that weight for a second. At 180 tons, this machine is significantly heavier than the largest animal to ever live on this planet. So when we say they're moving it, they are literally moving a modern monument across continents.
So, the machine makes it across the world. Mission accomplished, right? Not even close. In fact, a whole new phase kicks off, and it requires what is basically an on-site army just to get the thing running, and, more importantly, to keep it running.
Yeah, this is not something you just, plug into the wall and flip a switch. A whole team of ASML's top engineers will be on site for months, meticulously putting every single piece back together and calibrating it all to absolute perfection.
And their job is never really done. See, the goal is to keep these machines running with over 95% uptime. In this industry, every single second of downtime costs a fortune, so hitting that number is this relentless 24/7 effort. So how do you actually hit that 95% target? Well, ASML literally embeds thousands of its own engineers inside its customers' chip factories, permanently. This goes way beyond customer service. It's a deep, continuous partnership that's woven right into the fabric of the global tech industry.
But when you step back and look at all this, the giant machine, the insane logistics, the clean rooms, the on-site army, you start to realize something. The machine itself, as amazing as it is, isn't the real secret to ASML's dominance. The real secret is the human blueprint.
It's the brain power. ASML is like a talent magnet, pulling in top PhDs from all over the world, experts in physics, optics, mechatronics, material science, you name it. And they create this culture where these brilliant people are encouraged to constantly challenge each other, debate ideas, and push the limits of what's physically possible.
And we're not talking about some elite little group here. We're talking about over 40,000 employees. It's their shared, collective knowledge that actually builds, shits, and operates these impossible machines. Which brings us to this really key idea, something called tacit knowledge. Now, this isn't the stuff you find in a manual or a textbook. It's the know-how you get from experience. It's that gut feeling, that intuition that comes from doing something for years and years. It's the knowledge you can't just write down.
And that right there, that is ASML's ultimate superpower. It's their real moat. Because even if a competitor got their hands on the exact blueprints, they wouldn't have the thousands of people with the tacit knowledge of how to actually build it, how to fine-tune it, and how to make it all work. The machine is just the physical result of all that human knowledge.
What if I told you that at the very heart of the tech war between the US and China, the most important piece on the board isn't a weapon or a policy, but a single obscure company?
You know, when you hear the term global choke point, you probably think of something like the Suez Canal, right? A narrow shipping lane where one little problem can cause a worldwide headache. But what if the most important choke point of our time isn't a place on a map at all?
Yeah, that's right. It's a company. One single firm that holds the keys to the future of, well, pretty much everything, from the phone in your pocket to the most powerful AI and military systems we can imagine.
So how in the world does a company become a geopolitical weapon? Well, it all comes down to the new battleground between the US and China, the chip war. This is a fight for nothing less than total technological dominance.
So around 2018, as things started to really heat up, American strategists had this kind of aha moment. They figured out that the key to slowing down China's tech ambitions wasn't about stopping the finished chips themselves. No, it was about controlling the one single thing you absolutely need to make the most advanced chips. And every road led them to one place.
And that one place is a Dutch company called ASML. So, with a monopoly that powerful, you can see why it became the focal point of the US containment strategy. Once Washington zeroed in on this choke point, the question was pretty simple. How do you actually control it? How can the American government tell a Dutch company what it can and can't sell?
Well, the answer is a really powerful and kind of obscure bit of trade law called the Foreign Direct Product Rule, or FDPR. It sounds complicated, but the idea is simple. If a product made anywhere in the world contains a certain amount of American technology, the US gets a say in where it goes.
So how does that apply to a company in the Netherlands? Well, it turns out that even though ASML is European, its machines are a global puzzle. They have absolutely critical parts, like their light source, that come from an American company ASML bought years ago. Plus, they rely on key patents from a US research group. And that's the hook. That's the leverage the US needed.
And boy, have we seen them use that leverage. First, under the Trump administration, the US leaned on the Dutch government to block sales of those top-tier EUV machines to China. Then, in 2023, the Biden administration tightened the screws even more, expanding the ban to include the most advanced versions of the older DUV machines too. The message was clear. We're widening the tech gap.
Okay, so what happens when you turn off a technology spigot like that? The ripple effects were immediate, and they put both ASML and China in a really tough spot.
For ASML, the business hit is just huge. I mean, China wasn't just some small market for them. It was consistently one of their biggest, accounting for a massive 30 to 40% of their sales recently. You just can't shut off a customer that big without feeling it.
The company itself is predicting that these new export rules will impact about 10 to 15% of their sales to China in 2024. We're talking about a multi-billion-dollar hit, all because of geopolitics.
But for China, the consequences are way more severe. This ban on advanced machines basically puts a hard ceiling on their entire domestic chip industry. It physically stops them from being able to mass produce the most advanced chips needed for world-class AI or the next generation of smartphones.
And the reaction inside China was telling. It was basically a mad dash. Reports came out describing Chinese chip makers engaging in panic buying, just grabbing as many of the older, less restricted machines as they possibly could before the new rules locked them out. They were stockpiling for a very uncertain future.
But all of this pressure, this panic, it's having an unintended side effect. And this might be the most important part of the whole story. It's kicking off a furious race to create a competitor to ASML. The short-term pain for China might be creating a massive long-term problem for the West. Just think about it for a second. By cutting China off from the global supply, the US and its allies are basically giving Beijing the world's biggest incentive to build its own supply chain. This is no longer just a commercial goal for them. It's a matter of national survival.
And that's exactly what's happening. China is now pouring unbelievable amounts of money and resources into its own companies, like Shanghai Microelectronics, with one single goal: catch up. Now, to be clear, they are decades behind ASML. The mountain they have to climb is enormous. But now, climbing it is a top national priority. And this brings us to the great paradox of this whole thing. The very strategy designed to contain China's tech ambitions and keep them dependent on the West, well, it might just end up creating the one thing the West fears the most: a completely independent, powerful competitor who doesn't need them for anything.
Welcome to The Explainer. Today, we're diving into the absolutely mind-bending physics that goes into building the chips that power, well, everything. It's a story about creating conditions literally hotter than a star, inside a vacuum more perfect than deep space, all to work with a kind of light that just breaks all the normal rules of optics.
So let's just jump right in with the big question. How do you handle light that gets soaked up by pretty much everything it touches, including the air itself? Seriously, solving this single massive problem is what unlocked the entire future of computing. This wasn't just some engineering puzzle. It was a head-on battle with the laws of physics. You see, to keep making transistors smaller and smaller down to the atomic scale, the industry hit a brick wall. Progress meant that engineers had to throw out everything they knew about light and optics and basically embrace a whole new kind of physics. And this slide right here really puts the challenge into perspective. The old light, called DUV, had a wavelength of 193 nanometers and acted like a predictable wave. You could shine it through glass lenses, no problem. But this new UV light, it's a different beast entirely, at just 13.5 nanometers. This wasn't just an upgrade, it was a complete disruption. The old rulebook just didn't apply anymore. I mean, think about that for a second. The very nature of light changes. It becomes so energetic, so reactive, that it stops acting like a gentle wave and starts acting more like a tiny, super fast bullet. And well, that meant a whole new set of rules and a whole new list of problems that sounded completely impossible to solve. So, okay, you need this extreme particle-like light to etch the world's most advanced chips. How on earth do you even make it? You can't just go out and buy an EUV light bulb and flip a switch. Nope. You have to forge it from scratch, moment by moment. Now, here's the crazy part. That 13.5 nanometer wavelength wasn't chosen because it was convenient. It was dictated by the fundamental physics of one specific element, tin. It just so happens that when you blast a tin atom with an insane amount of energy, enough to rip away up to 13 of its electrons, it screams out a burst of light at that exact perfect wavelength. And to get tin to give up that light, you need an environment with an unbelievable amount of energy. We're talking about creating a tiny ball of plasma that hits temperatures over 200,000 degrees Celsius. You're basically recreating the conditions you'd find in the atmosphere of a star. So how do you do it? The process is just staggering. A tiny droplet of molten tin, way smaller than a human hair, gets shot through a chamber. First, it gets zapped by one laser to flatten it out like a pancake. Then, an instant later, a way more powerful laser hits it and just vaporizes it into that star-hot plasma. And get this? That two-step bullseye happens 50,000 times every single second. So you've done it. You've figured out how to forge a microscopic star 50,000 times a second to create the light you need. Incredible. But now you have to actually guide that light onto the silicon wafer. And that's where you run into the next seemingly impossible problem. And this right here is the roadblock. For centuries, optics has been all about bending light with glass lenses. But EUV light is so high energy, it doesn't pass through glass. It just gets absorbed. That meant the entire foundation of optical engineering, everything we knew, had to be thrown right out the window. So if you can't pass light through anything, what do? Well, your only option is to bounce it. The solution was to build an entire system made of mirrors. And we're not talking about your bathroom mirror. These are the smoothest, most perfect, most ridiculously precise reflective surfaces ever created by humanity. But the light's tendency to get absorbed created yet another massive engineering headache. It wasn't just absorbed by solid stuff like glass, it was also absorbed by the very air we breathe. It turns out, solving one problem just created another, more subtle one. To keep the light from getting absorbed by air, the entire machine has to operate in a hard vacuum. But now, in that vacuum, the very materials the machine is made of, the cables, the sensors, everything, start releasing tiny trapped gas molecules. And these stray molecules act like a poison, coating those priceless mirrors and killing the light. This whole phenomenon is called outgassing, and it's a silent enemy inside these systems. It means every single component, right down to the last screw and wire, had to be engineered from special, ultra-pure materials that wouldn't shed these contaminating molecules in a vacuum. But even with a near-perfect vacuum and all these special materials, there's one particular contaminant that's a constant threat, slowly poisoning the machine from the inside out. And that enemy is carbon. Even a handful of stray carbon-based molecules is a total disaster. The intense EUV light can actually crack them open, and that deposits a microscopic layer of graphite, basically soot, right onto those perfect mirrors. It absorbs the light and grinds the entire multi-million-dollar operation to a halt. So to fight this, the system has this active cleaning module that is it's brilliant. It continuously floods the mirrors with something called hydrogen radicals. These are super reactive hydrogen atoms that act like the universe's tiniest janitors, chemically scrubbing the carbon gunk off the mirrors while the machine is still running. Let's talk about mirrors, but not your bathroom mirror. We're talking about pieces of technology so perfect, they make a surgeon's scalpel look like a butter knife. These things are engineered to control light at an almost impossibly small scale, and honestly, they're the secret ingredient inside the most powerful computer chips on the entire planet. So, let's get into it. Everything starts with a central problem. A paradox, really. The very light you need to etch microscopic circuits onto our chips, it's a special type of light called extreme ultraviolet, or EUV, has this really frustrating habit. It gets absorbed by pretty much everything it touches. Mirrors, lenses, you name it. So how in the world do you build a mirror for a type of light that refuses to be reflected? Okay, here's the core of it. At the tiny wavelength of EUV light, we're talking just 13.5 nanometers. Even the shiniest materials you can think of, like perfectly polished gold, they just stop working. They don't reflect. Instead, they act like black paint, just soaking up all that precious light. And since lenses also absorb it, engineers realized they needed a completely new kind of mirror. And the answer is something called a distributed Bragg reflector. Now, this is not a single polished surface. You have to get that image out of your head. This is a totally different class of optical technology, engineered literally atom by the geniuses at ASML and Zeiss. And it works by using a really, really clever principle in physics. So how does it work? Well, it's not about one surface. It's about many. The mirror is actually a stack of incredibly thin, alternating layers. As light comes in, just a tiny bit reflects off the boundary of each layer. But here's the magic. The layers are spaced so perfectly that all these tiny little reflected waves line up exactly in sync. They build on each other, they amplify each other, creating one single strong reflected beam. It is the textbook definition of constructive interference. The precision needed to build this it's mind-boggling. We're talking about a stack of up to 100 alternating layers of two different materials, molybdenum and silicone. The thickness of every single layer has to be tuned to exactly 1/4 of the light's wavelength. If you're off by even a fraction of a nanometer, and I mean the width of just a few atoms, the whole effect just collapses. The mirror goes dark. The tolerances are, to put it mildly, unforgiving. Now, even with that level of atomic perfection, the absolute best-case scenario for one of these mirrors is reflecting about 70% of the light that hits it. So what happens to the other 30%? Well, it gets absorbed by the mirror as heat, which, as you're about to see, creates a whole new set of massive problems. And that 70% reflectivity number has a staggering consequence. You see, an EUV machine doesn't just use one mirror, it uses a whole train of them to guide the light. After bouncing off just 10 of these mirrors, only 2.8% of the original light is actually left. This is why the light source for these machines has to be so ridiculously powerful. It's literally a high-power laser blasting tiny droplets of molten tin to create a plasma, all just to get a tiny fraction of that energy onto the final silicon wafer. But okay, let's say you've figured out how to reflect the light. That's only half the battle. For the image you're projecting to be perfect, the mirror's surface has to be perfect too. And that means creating what is, with no exaggeration, the flattest object ever made by human hands. To give you a sense of just how flat we're talking about, the engineers behind this have this just stunning analogy. Imagine one of these mirrors was scaled up to be the size of the entire country of Germany. The biggest bump, the tallest mountain on that entire surface, would be smaller than the thickness of a single piece of paper. We are talking about smoothness measured in picometers. That's trillionths of a meter. You just can't get that kind of perfection with old-school grinding and polishing. Those traditional methods always leave tiny errors, and they actually damage the material just below the surface. So instead, Zeiss uses a process called ion beam figuring. They scanned a focused beam of ions across the surface, which is basically like sandblasting it one single atom at a time to shave off any and all imperfections without leaving a single scratch. So what's this perfectly flat surface made of? Well, the base material, the substrate, is a special glass ceramic called zero-Gur. And it has a superpower that connects right back to that heat problem we mentioned. Zero-Gur has pretty much zero thermal expansion. This means that even as it's getting blasted with intense heat from that EUV light, it absolutely refuses to warp or change its shape. All right, so now we have a multi-layer mirror that is atomically flat. But now it has to actually do its job while getting hammered with intense energy. This brings us to the next set of challenges. How do you manage all that heat? And how do you eliminate any possible vibration? Remember that 30% of light that gets absorbed as heat? That's a huge problem. It can cause tiny deformations on the mirror's surface, a problem called thermal lensing that would totally blur the image. To fight this, engineers use this cool two-pronged attack. First, they have internal microchannels that circulate cooling water through the mirror. But, and this sounds crazy, they also use heaters to keep the entire mirror at a very specific uniform temperature, the exact point where that zero-Dur material has zero thermal expansion. So you cool it and you heat it at the same time to keep it perfect. And on top of all that, get this, these mirrors aren't just bolted down, they're essentially floating. They sit on a series of active actuators that can adjust their position and tilt in 6 different directions with nanometer precision. This whole system is constantly working in real time to cancel out any vibration or thermal drift, keeping that optical path absolutely flawless. Of course, progress never stops. To print even smaller, even faster chips, engineers had to push the laws of optics even further. This led them to the next generation, called high-NA systems, and a bizarre new challenge that required them to literally twist the nature of the image itself. So here's the next physics puzzle. To get a sharper, more detailed image on a chip, you have to collect light from wider and steeper angles. You can think of it like a camera lens. A wider aperture gives you a sharper focus. The problem is, in this system, if the light hits the chip's blueprint, which is called a mask, at too steep of an angle, the tiny patterns on that mask start casting shadows on the silicon wafer below, which just ruins the entire process. The solution is this incredibly clever but weird optical workaround called anamorphic optics. You see, while the standard systems magnify the image evenly, 4 times in both directions, these new high-NA systems actually stretch the image. They magnify it 4 times in one direction, but 8 times in the other. This strange trick solves the shadow problem right at the source. Now, this anamorphic design is a brilliant optical trick. It keeps the angle of light at the mask manageable while still getting that super high resolution down at the wafer. But it comes with one huge consequence. You can only print half a chip at a time. The machine literally has to print one half, then quickly move and perfectly stitch the second half right next to it. And that creates a just immense mechanical engineering challenge. To print chips fast enough using this 2-pass method, the stage that holds the blueprint has to accelerate at a mind-bending 32 Gs. To put that in perspective, that is way more G-force than a fighter pilot can withstand. It's just an incredible feat of engineering.
How on earth do they achieve such insane precision? Well, in this explainer, we're going to dive right inside one of these systems, and you're going to see that it's not just printing chips, it's constantly measuring and correcting itself in this absolutely mind-blowing feedback loop.
Right off the bat, let's clear up the biggest misunderstanding about these machines. Thinking of them as just super precise printers, that's like calling a Formula One car just a car. The reality is so much cooler and way more complex.
Okay, think about your desk printer. It gets a command, it puts ink on paper, it's a one-way street, right? An ASML machine, on the other hand, is what you'd call a cyber-physical system. It doesn't just print. It prints, then it immediately measures what it just did, senses its own errors down to an atomic level, and then it actively corrects for those imperfections on the very next layer. It's a constant conversation, not just a one-off command.
So why go through all this trouble? Why is all this complexity so necessary? It's because when you're building transistors and circuits with features smaller than 10 nanometers, your margin for error, well, it basically disappears. It's pretty much zero. The tiniest drift, a subtle change in temperature, any of that can completely wreck a multi-billion-dollar chip. The real challenge becomes, how do you even see, let alone fix, errors that are practically invisible?
So the first part of the solution is a system that acts as the machine's fast eye, and is called scatterometry. The name of the game here is speed. You have to measure thousands of different points all across that silicon wafer, and you have to do it fast enough to keep up with production. You can't just hit pause on the assembly line, you know?
So, what exactly is scatterometry?
Well, it's a totally brilliant optical trick. Instead of trying to take a direct picture of these tiny features, which would be way too slow, the system shines a beam of light onto a special target on the wafer. Then it analyzes how that light scatters back. Every single tiny variation in the structure creates its own unique pattern, basically a fingerprint of light.
Here's the play-by-play. First, a beam of light hits the target area. Second, the machine's sensors read that unique scattered pattern. Now here's the magic step. Number 3. It compares that real-world pattern to a massive digital library of pre-calculated, simulated fingerprints. By finding the closest match in that library, the system can reconstruct the actual physical shape of the circuit with, and this is wild, sub-nanometer accuracy.
So what is it looking for with all these light fingerprints? Well, this system, which is called YieldStar, is laser-focused on 3 critical things. The first is overlay. That's just making sure each new layer lines up perfectly with the one underneath it. Second is focus. Pretty self-explanatory. And third is dose, which is checking that the exact right amount of light energy was used. YieldStar measures all of this at just incredible speeds.
Okay, so we've got this super fast system that uses these clever models to check for common errors. It sounds almost perfect, right? It's great for finding predictable problems. But there's always a but. What about the unpredictable stuff? What's the catch? What can't this light-based system see? And that brings us to the second piece of the puzzle, the E-beam. This is the machine's other eye, the slow, super methodical, incredibly precise eye. This is what you use when you absolutely positively have to see the ground truth of what is actually on that wafer.
See, the problem is that those optical models, as smart as they are great at seeing the average shape of a structure. But they can be totally blind to random one-off screw-ups, what engineers call stochastic defects. Think about a single circuit line that just randomly breaks, or maybe 2 lines that accidentally touch, creating a bridge. The light-based system can just miss that entirely.
And this really shows you the fundamental trade-off. You've got YieldStar's optical system on one hand, which is blazing fast, but it's model-based, so it really sees the average shape. Then you have the E-beam. It's much, much slower, but it uses a focused beam of electrons to take a direct image. It doesn't need a model. It just shows you exactly what's there, the ground truth.
So what do? You have a fast eye and a slow, hyper-accurate eye. You obviously can't use the slow one for everything or you'd never finish a single wafer. The genius solution is to make them work together in a perfect partnership, where you use the slow system to teach the fast system.
And this is absolutely crucial. The data you get from that super accurate E-beam isn't just for flagging a few random flaws here and there. No, it's fed back to calibrate and constantly improve the models that the fast optical system relies on. It's basically like the E-beam is the expert tutor, giving the fast system the answer key so it can get smarter over time.
So how does it do that exactly? Well, for one, the E-beam verifies hotspots. These are tricky little areas in a chip's design that are notoriously difficult to print correctly. It also provides real-world, ground truth data that makes the optical simulations way more accurate. And all of this works together to create a nearly perfect digital twin of the physical wafer.
But all of this amazing measurement technology, all this data, is completely useless if you can't do something with it. And this brings us to what is, for my money, the most incredible part of this whole process: closing the feedback loop and turning all that data into direct physical action. We're not talking about data for a spreadsheet that some engineer looks at next week. No way. This information is fed directly back into the lithography machine's main control system, in real time. The machine knows as it's working on the next layer that the wafer it's holding is maybe slightly warped from heat, or that the previous layer has a tiny, subtle distortion.
And here's what it does about it. The stage that holds the silicon wafer, itself an absolute marvel of engineering, doesn't just move from point A to point B in a straight line. If an error is detected, it can physically trace a complex, compensating path during the light exposure to completely cancel out the error from the previous layer.
A quote from the source material puts it in a way that's just perfect. It says, "The stage wiggles the wafer." Now, this isn't some random vibration. It is an incredibly precise, pre-calculated wiggle that physically deforms the printing path in real time to perfectly match whatever distortion exists on the layer below it. It's mind-boggling.
We are diving deep, deep inside some of the most advanced factories on planet Earth to uncover a hidden war. And no, it's not a war with robots or machines. It's a war of pure information, an invisible fight where literally trillions of lines of code go head-to-head with the fundamental laws of physics. All of this just to build the chips that run our entire world.
So to really get what's going on here, I've got a question for you, and it's one that sounds completely impossible. What if the blueprint for a computer chip, the actual pattern you want to create, looked absolutely nothing like the finished product? I know, it sounds absurd, right? But this is the bizarre reality at the cutting edge of making technology.
So why this weird situation? Well, it all comes down to one big problem, an enemy that engineers have been battling for decades: the physics of light itself. The specific villain here is something called diffraction. Think about it like this. When you try to shine light through a ridiculously tiny opening, and we're talking about openings that are smaller than the wavelength of the light you're using, that light doesn't just go through in a nice clean beam. Nope, it bends, it spreads out, it gets all blurry around the edges. So what this means in practice is, chip designers might want to print a perfect square with these beautiful, sharp 90-degree corners. But when they shine that special light through the stencil or the mask, diffraction takes over and turns that perfect square into a mushy, rounded, blurry blob on the silicon wafer. And let's be honest, you can't build a supercomputer with a bunch of blobs. So since they couldn't just, rewrite the laws of physics, engineers had this absolutely brilliant idea. If the light is going to mess up our pattern, well then let's mess up the pattern first, but in the exact opposite way. It was time to fight back. It was time to fight physics with code. And this is where we get to the magic. It's a technique called computational lithography. Basically, it's all software that reverse engineers the whole problem. The code simulates exactly how the light is going to get blurry, and then it creates a pre-distorted mask that looks kind of weird. But once physics does its blurring thing, it snaps into focus as the perfect shape you wanted all along. And check this out. This is where things get really wild. To print a simple, boring rectangle, the software might come up with a mask that looks like a bizarre dog bone, and it's surrounded by these tiny, separate little dots that don't even get printed on the chip. These are called assist features, and they're only there to bend the light in just the right way to form that perfect rectangle. It's just an absolutely stunning example of fighting nature with pure math. Okay, so this worked beautifully for a while, but you know how technology goes. As chips got smaller and way more complex, this brilliant software solution started to create its own monster of a problem, a full-on computational crisis. See, to print the teeniest, tiniest features for the chips in your phone today, the simple fixes weren't enough. Engineers had to go to the next level, an even more powerful technique called inverse lithography technology, or ILT. And it took a totally different approach. Instead of using a set of pre-programmed rules, ILT does something that sounds insane. It treats the entire mask as a giant grid of millions upon millions of pixels. Then, an algorithm works away, optimizing every single one of those pixels to create the absolute perfect, mathematically ideal mask. The final result looks less like an engineering blueprint and more like, something you'd see under a microscope. But the price for this kind of perfection? Oh, it was just staggering. To generate just one of these advanced masks, it could take weeks of non-stop processing time, running on huge, expensive computer clusters. And that was just for one part of one chip. Across the whole industry, chip makers were burning through, get this, more than 10 billion CPU hours every single year, just on this one task. It was completely out of control. And look, this wasn't just some inconvenience, right? This was a 5-alarm fire. The time and the money it took to design these masks was getting so big that it threatened to bring the entire engine of progress, Moore's Law itself, to a grinding halt. But just when it looked like we were going to hit a brick wall, a massive breakthrough happened that completely changed the game. And it happened because some of the biggest names in the industry decided to work together. You had the company that makes the machines, ASML, teaming up with the GPU kings at NVIDIA, the world's #1 chipmaker, TSMC, and the top design software company, Synopsys. They all realized, wait a second, the kind of math we need to simulate light is perfect for the way a GPU works. And this chart just says it all, doesn't it? They built this incredible software library called Litho, and what used to take weeks and weeks on a massive cluster of CPUs could now be done in a tiny fraction of that time on GPUs. How much faster? We are talking a mind-blowing 40 times faster. This wasn't a small step. It was a giant leap that jumped over the entire problem.
And this quote from one of the sources just nails it. This speed up wasn't just a nice to have, it was an enabler. Without it, the cost to compute the mask for a next-generation chip would have been so high it just wouldn't have been profitable to make them. The GPU quite literally saved Moore's law. Okay, so the code has won. The perfect mask is designed. Awesome. But that's only half the battle. Now you gotta ask, what kind of machine, what kind of brain can even run this whole impossible process? And this brings us to the final, and maybe the most mind-bending, layer of this invisible war. The software that acts as the machine's central nervous system. It is, for all intents and purposes, an impossible brain. Just try to wrap your head around what this software is doing 24/7. It's juggling millions of different parameters. It's firing a super high-powered laser 50,000 times a second. It's moving the silicon wafer and the mask at the same time with a level of precision that is just hard to comprehend. And this is all run by millions of lines of code that absolutely, positively cannot crash, ever.
And why can't it crash? Well, because a single one of these machines costs nearly $400 million. A software bug isn't just a glitch that makes you restart your computer. It's a potential $500 million catastrophe. There is zero room for error. In fact, the software has gotten so unbelievably complex that no single human being on Earth fully understands the entire code base anymore. It's true. The company that builds them, ASML, is now using AI, large language models, just to help their own world-class engineers maintain and work on the code.
All right, let's get right into it. We're diving into the world of mechatronics, but this isn't your everyday robotics class. We are talking about the art of extreme motion. Think about combining impossible speed with, well, impossible precision. And this all happens deep inside ASML's mind-blowing lithography machines.
So to really get a handle on what we're dealing with, check out this analogy. You've got this platform inside the machine, right? It's called the wafer stage. And its job is to do something that sounds completely bonkers. It has to accelerate like a Formula One car, stop on an absolute dime, and then position itself, get this, within the width of a single atom.
And here's the kicker. This isn't some delicate, one-time experiment in a lab. No way. The machine has to pull this off perfectly, thousands of times an hour, every hour, 24/7. I mean, the sheer relentlessness of it is almost as wild as the precision itself.
I know what you're thinking. This sounds like something straight out of science fiction, right? So how in the world is this even possible? Well, to figure that out, we have to start with one of the most basic, fundamental problems in all of physics.
Okay, first up, the first massive problem you have to solve is the battle against friction and force. You see, when you're working at the nanometer scale, any physical contact, and I mean any at all, is a complete disaster. The old ways of moving things, they're just not going to cut it.
Think about it. Normally, if you want something to move smoothly, you'd use something like a mechanical bearing, right? Ball bearings, maybe. But here, in this world, friction is the enemy. It creates heat, it creates wear. But it's even worse than that. Anytime two things touch, even if they're super smooth, you get tiny little particles. Basically, dust. And just one of those particles landing on the wafer can wreck an entire batch of chips. Oh, and on top of all that, they're just nowhere near accurate enough.
So that's the big question, right? If you can't touch it, how on earth do you move it? The answer is just elegant. Magnetic levitation. I mean, just look at this comparison. On the one side, you've got all the headaches of mechanical bearings. Friction, dust, inaccuracy, wear and tear. And on the other side, maglev. It solves everything. You get frictionless motion. Zero contact means zero particles. And you get this insane nanometer level control. So that's the first huge takeaway. To get this precise, you have to completely get rid of physical contact. Okay, so the stage is floating. Awesome. But how do you get that Formula One acceleration? Well, that's where something called planar motors come in. The easiest way to think about them is to imagine a powerful electric motor that you've sort of unrolled and laid out flat.
They use these crazy fast changing magnetic fields, kind of like a maglev train, to create this huge push. We're talking up to 7 Gs of force. And it does all of this without ever touching the stage. It's just pure, contactless power. All right, so here's where it gets really interesting. By solving the friction problem, they actually created a brand new one. See, this whole system has to operate in a super high vacuum. You can't even have air molecules bumping into things. But that clean, empty space, it brings a whole new set of problems you have to solve. I mean, really think about this for a sec. You have these ridiculously powerful motors generating a ton of heat. Here on Earth, you just, use a fan. Air cools things down. But in a vacuum, there's no air. There's nothing to carry that heat away. So how do you stop your multi-million-dollar motors from just melting? The solution is as brilliant as it is complex. You basically build the cooling system right into the moving parts. The engineers designed this whole network of tiny liquid cooling pipes that run directly through the floating stages. It's like a circulatory system for the machine, just constantly pulling all that waste heat away. But of course, that solution creates another mind-bending problem. Now you have physical hoses connected to a stage that's floating, that needs nanometer precision. Think about that. These hoses themselves have to be engineering marvels. They can't vibrate, not even a little. They can't push or pull on the stage at all. Any tiny little disturbance would throw the whole thing off and completely ruin the accuracy. It's just a perfect example of how, in this kind of extreme engineering, every solution introduces a new and sometimes even harder problem to solve. Okay, so we've tackled the massive forces, the Gs, the movement. Now let's zoom way in, down to the microscopic level. We figured out how to move the stage, but the silicon wafer sitting on it? Well, that introduces a whole new, super delicate problem: temperature. And when I say perfect, I mean perfect. We're talking about a temperature difference of just a few millikelvins. That's thousands of a degree. If the temperature is off by that tiny amount, the wafer will expand or contract just enough to throw off the alignment and ruin the whole thing. The whole wafer just gone. So how do they deal with that? With this really clever conditioning process that happens before the wafer even gets to the main stage. So first, it's placed on this special table. See how it's resting on those tiny little ceramic pillars? They're called burls, and they're there to minimize contact. Then, super precisely conditioned water flows underneath the table, and that brings the wafer to the exact temperature it needs to be. And the best part? This whole thing takes just a few seconds, because you got to keep the factory moving. All right, so you think we've reached the peak of insane engineering, right? Wrong. Now we meet what I can only describe as the final boss. The next generation of these machines, it takes every single challenge we've just talked about and cranks the difficulty dial up to 11.
So, why the sudden jump in difficulty? It's all about synchronization. You have two main moving parts, the wafer stage we've been talking about, and the reticle stage, which holds the blueprint or the mask for the chip. In the new machines, to get the image printed correctly, that reticle stage has to move 4 times faster than the wafer stage, which, as we know, is already moving at an insane speed.
And that one simple requirement, that it has to move 4 times faster, leads to this number, 32 G. The reticle stage has to accelerate at 32 times the force of gravity. That is a force so extreme it pushes the absolute limits of what our materials can even handle. This chart really puts that jump into perspective. The wafer stage at 7G, that's already an engineering marvel. But the reticle stage? 32G. At that point, the problem isn't just about precision anymore. It becomes a brutal, raw physics problem. The question is simply, can you build something that won't literally tear itself to pieces under that kind of force? Yeah, because at 32G, you run into a classic engineering paradox. To survive that force without bending, the stage has to be incredibly stiff and rigid. But to accelerate that fast in the first place, it has to be incredibly light. And those two things, stiff and light, are basically opposites in the world of materials. This is why they have to use these super exotic materials like carbon fiber or silicon carbide, and they need clamps that can somehow hold the mass tight enough so it doesn't slip, but not so tight that it gets crushed by the G-force. The big takeaway here is that when you're at the absolute bleeding edge of performance, you are always fighting against the basic laws of physics.
So the first thing you've got to understand is that ASML isn't really a factory in the traditional sense. It's not stamping out widgets. A better way to think of it is as the central brain, the master architect coordinating this massive, sprawling, global operation. Now, the official term for what they do is system integrator. You know, a company that brings all the different pieces together and makes sure they work. But honestly, that term doesn't even begin to cover it. As you're about to see, it's so much deeper, so much more interconnected than that simple definition lets on. And this right here gets to the absolute core of their strategy. ASML only makes about, say, 15 to 20% of the machine's parts themselves. The other 80%, the vast majority, comes from this incredible network of highly specialized partners. And when I say vast, I mean it. The scale is just staggering. We're talking more than 5,000 suppliers. Just let that sink in for a second. 5,000 different companies, all pouring their specific expertise into creating one single functional machine. It's wild. And look, it is so important to get this straight. This is not your typical supply chain where you just place an order for a part. No way. These companies are deep, integrated development partners. They work so closely with ASML that they might as well be internal divisions of the company. Okay, so within that giant network of 5,000, there's an inner circle, a core alliance that really forms the technological heart of the machine. These guys aren't just any suppliers. They're the ones building the fundamental tech that makes the whole thing possible. It basically boils down to the so-called tripartite alliance. You've got ASML in the Netherlands, of course, handling the big picture architecture. And then you have two absolute powerhouses from Germany, Zeiss, the world's master of optics, and Trump, the go-to specialist for insanely powerful lasers. You take any one of these three out of the equation, and the machine just doesn't exist, period. The relationship with Zeiss is on a completely different level. They are the only company on the planet that can produce the impossibly precise mirrors and lenses needed for these machines. The partnership is so vital that ASML actually owns almost a quarter of the company. And get this, to create the optics for the newest machines, Zeiss had to build entirely new factories from the ground up, just to house the tools needed to make and measure these gigantic, flawless mirrors. Then you've got the laser from Trump. This is the monster that generates the extreme ultraviolet light, the light that actually etches the circuits onto the silicon. And it is an absolute behemoth. The laser system alone weighs over 20 tons. But here's the kicker. That one 20-ton laser system, it's made of 450,000 individual parts. I mean, that number just says it all, doesn't it? It's the perfect illustration of the kind of mind-bending complexity we're talking about here. Okay, so beyond that core German-Dutch alliance, there's this whole dense web of other suppliers that acts like the machine's nervous system. And a huge number of them are located right in ASML's backyard in the Netherlands. And the level of specialization is just incredible. You've got a major partner like the VDL Group, building the massive vacuum chambers and the super delicate robotic arms that handle the wafers. You have NTS doing mechatronics, others focused on vacuum R&D, precision sheet metal. Every single company is a world-class expert in its own little corner of the universe. So you've managed to get all these incredible, complex components built by thousands of partners. Fantastic. Now you've got to move them. This is the circulatory system, the truly monumental challenge of shipping this thing all over the world. And believe me, this challenge is only getting bigger. A standard EUV machine already takes up about 40 freight containers, which is a lot. But the next generation high-NA system, that explodes to 250 separate crates, needing 13 full-size trucks. The jump in logistical complexity is just enormous. When it's all packed up and ready to go, a single high-NA system weighs over 150 tons. Yep, that's our blue whale, just like we talked about at the beginning. So how on earth do you do it? Well, it's a process of extreme care. The most sensitive components, like those priceless Zeiss optics, are packed in special pods with active suspension to cancel out every tiny vibration. There are smart trackers on everything, monitoring G-forces, temperature, tilt, you name it, in real time. The whole thing gets flown in giant Boeing 747 cargo planes. And when it finally arrives, it has to be installed on factory floors that have been specially reinforced just to handle the immense weight. And this one detail really says it all. The tolerances are so insane that if a shipping crate is tilted just a few degrees too far during its journey, the warranty on a part that's worth millions of dollars could be instantly voided. The stakes are just unbelievably high at every single step. But here's the paradox. For all of its size and power and complexity, this global juggernaut is actually surprisingly fragile. It's facing a whole host of growing pressures from the outside world that threaten the entire delicate system. And this really gets to the core vulnerability of the whole enterprise, the concept of a single point of failure. When you have so much critical, can't get it anywhere else technology concentrated in one tiny corner of Europe, optics from Germany, assembly in the Netherlands, you create a pretty unique and serious risk for the entire global economy. And those challenges are piling up. You've got that geographic concentration risk we just talked about. You have rising geopolitical tensions and complex export rules restricting who can even buy these machines. You've got growing demands for sustainability. And on top of all that, you have the Dutch government launching massive initiatives, literally codenamed Operation Beethoven, just to make sure this vital company and its brain trust don't decide to pack up and leave. You see, the entire chip-making industry is slamming up against a physical wall. For a while now, to keep making transistors smaller and smaller, chipmakers have been using this, well, it's a clever but kind of brute force trick called double patterning. Imagine trying to draw an incredibly fine line, but your pen is too thick. So you draw it once, then you draw over it again, just slightly offset to get that thinner result. That's basically what they're doing. But here's the catch. It is super slow, it is ridiculously expensive, and honestly, it's a temporary fix. It's a bandage, not a cure. And that's where our hero comes in. This is the breakthrough that lets us leapfrog that whole messy process. We're talking about an 8-nanometer leap in a single go. And the jump here is just staggering. The current top-of-the-line machines use what's called extreme ultraviolet light, or EUV. They can get down to about 13 nanometers. This new generation, called high NA UV, just blows past that. It gets us all the way down to a mind-boggling 8 nanometers. Yeah, just let that sink in for a second. 8 nanometers. Being able to print circuits that tiny in one clean shot, it means we can cram billions and billions more transistors onto a single chip. We're talking about a whole new universe of performance and efficiency. This is literally the breakthrough the entire tech world has been holding its breath for. But, and you knew there was a but coming, right? When you're working at this kind of scale, solving one gigantic problem, well, it almost always creates a whole cascade of brand new, incredibly tough physics and engineering puzzles you have to solve. And this slide just lays out that chain reaction perfectly. So first, to get that 8-nanometer precision, you need all new, much bigger optics, okay? But second, these new mirrors aren't perfectly round. They're anamorphic, which is a fancy way of saying they stretch the light. This leads to problem number 3. The area you can print on the silicon wafer at one time gets cut in half, which of course creates a fourth, absolutely massive software problem. How in the world do you stitch those two halves of a chip together so perfectly that they're aligned down to the nanometer? Believe it or not, that's not even the biggest headache. Let's talk about this little component that you've probably never heard of, but it's absolutely critical. The pellicle. Think of it as an impossibly thin, perfectly clear dust cover for the master blueprint of the chip, which is called a mask. See, if even one tiny speck of dust lands on that mask, it's going to create a flaw on every single chip you print. The pellicle's job is to catch that dust and keep it out of focus so it doesn't get printed. It's the unsung hero of chip making. So what's the problem? Well, the new high-NA machines, they have to use a much more powerful light source to get the job done faster. And this creates a new arch nemesis, extreme heat. We're talking about so much thermal energy bombarding that poor little pellicle that the traditional materials would just poof, they'd melt. So that's kicked off this global hunt for a new super material. Polysilicon, that's the old standby. It just can't handle the heat anymore. Then you've got contenders like metal silicides, which are way more durable. But the one that really seems to be pulling ahead, the champion in this race, looks to be carbon nanotubes. Why? They're insanely strong, they're super transparent to the specific kind of light, and they handle heat like a champ. It's a full-on material science race against time. All of these insane challenges really point to something bigger. This isn't just about one machine sitting in a factory somewhere. What we're really looking at is a truly global machine. I love this quote because it just captures the essence of it perfectly. A mirror from Germany, a laser from Ditzingen, and math from California to print a transistor in Taiwan. I mean, come on, that's a fragile, beautiful miracle of global teamwork. And if you dig into it, this machine really represents 3 massive shifts. First, we're seeing this move away from just pure hardware. Now, getting that resolution depends just as much on insane amounts of math crunched by GPUs as it does on the physical mirrors themselves. It's computational physics. Second, you realize the supply chain is the technology. You can't just steal the blueprints for this thing. You'd have to replicate an entire global ecosystem built on decades of trust and specialized knowledge. Good luck with that. And finally, the new frontier, the new wall we're hitting, is all about heat. The biggest engineering fight is no longer just about making better lenses, it's about managing extreme temperatures with unbelievable precision.
Okay, so why should you care about this one, hyper-complex, super expensive machine? Because it is, and I mean this literally, printing our shared tech-fueled future. And the stakes here are just astronomical. The price tag for just one of these high-NA UEV systems, it's estimated to be around $400 million for one machine. And companies are lining up to pay that price because this one single platform, it's the key that unlocks pretty much everything else. The next great leap in AI? The supercomputers that will solve problems we can't even imagine yet. The next generation of phones, gadgets, and everything else in our lives? Yep, they all depend on this machine working. And that's what makes this the highest stakes race in all of technology right now. You've got Intel, who got the very first pilot system, desperately trying to use it to claw back its lead from the current king, TSMC. Make no mistake, the company that figures out how to master high-NA EUV first will almost certainly dominate the entire tech industry for the next decade. Which kind of leaves us with one last big provocative thought. So much of our technological progress, so much of the future we're all counting on, now rests on this one company, ASML, and this one type of machine. The power to literally build tomorrow is more concentrated than it has ever been. So you have to wonder, what happens if it breaks?